Thank you, Singh. Let me first add my 2 cents to what everybody else has said about Larry's work. To have someone who's as good as theory, experiment, and instrument design is quite remarkable. And when he asked me to participate in this symposium, I was really honored and immediately accepted. At that point, I thought, what am I going to talk about? I've been retired for almost 5 years. My last student left 2 years ago, and I would like to talk about something new. So then, it would be really nice if I could tie it in with something that with Larry's work as well. So at that point, I thought, well, I've been working with this student in our chemical and materials engineering department, Andy Weekly, and I first met him when I was on his master's committee, and he had a really, really good feeling for multivariate statistics, and so we started talking, and in the end decided that one area which really would be great to finally work a good way of doing it is for automated baseline correction of spectra. And so we started working on this. And as you will see, the method that he developed actually worked for bipolar spectra. Most of the spectra that we'd been operating on were this is serious. were surface enhanced infrared spectra. SEIRA spectra are unusual in that if the metal nanoparticles are not touching and you look at species on the surface of these metal nanoparticles, the spectra are perfectly symmetrical. They look like regular infrared spectra. Once the metal particles start to touch, the spectra are distorted. They look more like specular reflection spectra, and consequently are bipolar. So I thought, bipolar spectra, VCD, aha, got it. So this was the subject of my talk, and soon we'll get this thing hopefully set up. And no?
You have a stick?
I got a stick. Showing on the screen. Okay. Where are we?
Sorry about that, folks.
Is that right? Okay, good. So, let me. So now I'm working from this computer. Is there a way of advancing with this? Just advance on that. Okay. Go backwards. So, basically, all this work has been done by this very sharp grad student, Andy Weekly. His PhD advisor is my colleague, Eric Aston. And I've had fun just advising and talking about this. So let's go back to a little bit of VCD. I first really became aware of Larry's work when this paper was published in Applied Spectroscopy back in 1979. It was for anybody who's really needs to know what's going on in VCD, this is the paper. There isn't a single spectrum in there, but it covers the whole field. And this was when a young Max Dean was postdocing in his group. And basically the setup, as we've all seen, coming out of this paper was that the beam from an FTIR spectrometer was scanning relatively slowly, was passed through a linear polarizer, through the photoelastic modulator, and then onto the sample, and then you could split off the VCD and the regular spectrum, but the VCD spectrum was measured at a modulation frequency which is way higher than the Fourier frequencies of the FTIR spectrometer. And I thought this was a really neat idea, but kind of complicated. So, so then we thought up another way of doing this, and this is my one paper in VCD, as you will see why in just a minute. We thought that the whole reason for doing the sort of technique that Larry developed, or this technique, was to get around the dynamic range problem of an FTIR. You're talking about a signal, a differential signal, which is 4 orders of magnitude, 3 or 4 orders of magnitude at least, less than the regular spectrum. So it's very, very weak. So we thought that optical subtraction FTIR would be an interesting way of doing this. So the way that we came up with was to take the light from the source, collimate it, pass it into the interferometer a little off the usual axis, so that you could pick off both beams coming off the spectrometer, pass them through a polarizer, this time through a Fresnel ROM rather than a photoelastic modulator. And we're doing this with both beams, taking the beams, crossing them through the sample, so that both beams are passing through the sample, and then passing them onto the same detector. So basically what you're doing is you're looking at the detector is measuring the difference between the absorption of the two left and right polarized, circularly polarized light. And so here was the result. This is the spectrum of Camphor. And these are the spectra after subtracting the spectrum of the racemic mixture of the two enantiomers. And we thought this was pretty good. I mean, this is what you should see. You should see the spectra going in opposite directions. And then we actually compared them with what Larry had measured on his technique. And this is one of ours, and this is the spectrum of Larry's, and they are obviously very different. There are some similarities. This was actually measured at higher resolution, so these two bands are sharper. But you can see some bands which are there, but but the artifacts are as big as what you're looking at, as what you want to see, and so ultimately it was. The big problem is one of optical alignment with this system. You've got this massive optical path length, and they've got to be identical. I mean, they've got to be completely complementary to cancel everything else out, and it just proved to be extremely difficult to do this, and we never managed it. So that was my that was my little foray into VCD, and my first recognition that Larry Nafee was a pretty sharp guy. And still is. So why do VCD? So this talk is about baseline correction, really, and so why do VCD spectra need baseline correction? Well, I think one of the first reasons is that if you want to calculate an antinomeric excess in a routine manner, you really want a baseline corrected spectrum. And I think this is the most important thing. If all you're doing is looking at absolute configuration, a bad baseline doesn't really affect you that badly. Bands go up, bands go down, you can do the comparison. And to remove, maybe to remove solvent artifacts as well. So, oh well, can't go backwards. That was what I just hit. It's not doing it. So, I wish I could go back, but nonetheless, don't worry. let's see how typically baseline correction techniques are applied. You have a spectrum with a bad baseline. This happens to be a Raman spectrum, and it's noisy. You've got some algorithm which calculates a baseline. You subtract the baseline from well, one more. Okay, thanks. So what we got, so back up just a little bit, sorry about that, we contacted BioTools, and Larry's son, Jordan, works there, and he sent us these spectra, because we specifically asked for spectra with bad baselines. Now, I know the dual PEM technique is meant to get rid of baselines completely, but these are the ones that he sent us. And so there's a baseline problem in both of these spectra. They don't look bad until you look at the ends. And there are two regions of this which are bad. One is the carbonyl band, and the carbonyl band is totally absorbing in this case. This is a 100 micron cell with about 10% of camphor in there. So that's about 10 microns of camphor, and that's enough to pretty much saturate the carbonyl absorption. And you can see in one spectrum this is a sharp artifact going up, and the other one is going down. So it's clearly artifactual. The other one is these are carbon tetrachloride solutions, and where carbon tet starts to absorb, you also get a very, very bad baseline. So you've got a relatively easy problem, what looks like a relatively easy problem of baseline correction over most of the spectrum, with the difficulty on either end. And many baseline correction routines are looking for minima. And that minimum and that minimum are clearly out of whack. Okay, so going back to the slide that I was talking about before, the algorithm typical algorithm will calculate a baseline in some way and subtract that baseline from the spectrum, leaving yourself a baseline corrected spectrum. And so this is a generic side, but there are many ways of doing this. Some are manual, and the manual ones are fine, except they're manual, and it requires a certain level of operator bias to select the right points that you select as baselines. But there have been a number of automated methods which have been described, and Husheng Yang, who's in the audience back there, has got together a number of these. Husheng was in my group, now works with AstraZeneca, and he promised me a paper on automatic baseline correction many years ago, and it was good enough to finally come through with this, and I've sat on it for a couple of years. It was for various reasons. Husheng, I guarantee this will be submitted this year, sometime. But these are just some of the methods that have been described for automated baseline correction. I'm not going to get into how they work, but all of them actually have some level of problem. And Husheng developed a sort of score method. This is somewhat subjective on here, from really good to really bad. And so the middle score, score 3, shows some difference from the original, but it's not much better. So we started off, one of the ways we started off was to look at some really bad spectra that had been measured in our lab. The late Thomas Hirschfeld had made a suggestion many years ago. He said that everybody who works in spectroscopy should keep a library of spectra that he called the Chamber of Horrors. If you measure a bad spectrum, don't throw it away, stick it in the Chamber of Horrors, sometime you may use it. And so these were some of our Raman Chamber of Horrors. They're mainly fluorescence backgrounds. And it turns out that Raman spectra are pretty easily baseline corrected. So most of these techniques worked. So here, for example, is an iterative stripping method, and it gives you still not a perfect, it's a better baseline than this, but it's still not a perfect baseline. Score is 4. There's another method called the Minima method, and this was the most difficult one to baseline correct. The Raman spectrum could only just be seen above the fluorescence. It was noisy, and so you can get little spikes on the spectrum, distortions to the spectrum, and so this is not much better than the original. The more difficult ones to baseline correct were these surface-enhanced infrared absorption spectra, where the metal nanoparticles were close enough to give rise to be at what's called the percolation limit, and in this particular case, you get bipolar spectra, and many of the various methods, automated baseline correction methods, don't work very, very well. Sometimes you even have, we even found ones with spikes in, really large negative going spikes in the spectrum like this, in the middle of the spectrum, as opposed to the outer limits where we could ignore it. This last one here looks, it's just a bad baseline and a bunch of water vapor on there. So how did that one work? Well, the iterative stripping method gives you some correction, but really not very much at all. Maybe it's even worse. Score of 2. Neighbor comparison is another iterative method, and in this case, again, it gives you a wavy baseline. In this particular, this is an iterative method, and if you actually give it fewer iterations, you get better baseline correction. So coming up with the right parameters can sometimes vary from spectrum to spectrum. If you look at another one of these called ultra-low frequency filtering, again, under certain circumstances, you get good baseline correction. Under other circumstances, you get lousy baseline correction. Again, it depends on the operator's choice of parameters. We wanted to get away from that. So the final one that I'd like to mention is Brooker's rubber band, so-called rubber band method. As someone who sees a lot of papers coming into to applied spectroscopy, it is now called the well-known rubber band method to most authors. It has never been published, and we don't know how this worked. So Andy thought, well, I'm going to guess. And the first thing he did was to split. We knew that the spectrum was split up into 64 different segments on there, and then after that he winged it and came up with something that was not the rubber band method. But in this particular case, here rubber band correction gives a very good baseline correction for bands where all the for spectra, excuse me, where all the bands go in one direction. And if you look at this, there is no, it's all positive. Everything, all the baseline is a positive baseline. But the baseline is in fact a little bit above that, because it's the most negative parts of the spectrum are due to noise. Looking at the SEIRA spectrum, which is one that I really wanted to look at, the first thing they did, being good spectroscopists, was to do a Kramer's conic transform, which was the last thing I wanted, unfortunately. But again, even after Kramer's conic transform, there was still some distortion of these bands. And again, you can see, if you look carefully, that this is really all positive. And so working with this sort of technique does not work with bipolar spectra. So this led to this development of a technique which we described last year in applied spectroscopy in this particular paper here, and so how does this work? Spectrum is divided into 64 regions. You locate the minimum in each region. You calculate the second derivative in each region. And if the difference in slope is larger than the difference in slope for the previous baseline points, then it's assumed to be a band. And so here's a spectrum where you're showing the difference in slope. Here's something that's clearly on a band, for example. And then going on from there, if the absolute difference in slope between the current value is larger than the next point, which was assigned as a band, then that point is also assigned as a band. And then, so it's rejected as being a baseline point. And so you're looking at regions there to try and find the baseline points in an automated and non-subjective fashion. Does that work? Well, let's first of all try it with a Raman spectrum with a fluorescent background. And this is the calculated baseline. This is the spectrum. Obviously, really nice baseline correction. In this particular case, we'd been working with this Raman spectral explosive, so TNT and Semtex are two of the samples that we were looking at. The Semtex has a much larger fluorescent background, and so this was a somewhat more difficult one for most baseline correction routines to handle. But I'll show this expanded. This is the result. And so what you can see is that there are still some negative features on there which stay negative because they're actually spikes which are a real part of the spectrum. So it actually worked very, very well for Raman spectra. Just to tie in with what Bruce was talking about, this particular group that Andy's working with is one of the things they're looking at is electrospinning of polyvinyl pyrrolidone and titania with titania fibers. And this was the terrible Raman spectrum, one of the earlier spectra that they did, where we applied this baseline correction technique to get, I mean, for this rather poor, noisy spectrum, a pretty decent baseline correction. So what about bipolar spectra? Well, here's a spectrum of parafluorothiophonol chemisorbed onto silver nanoparticles beyond the percolation limit in size, and you can see that it actually selects the baseline pretty well. And again, this is using the same parameters that we use for Raman spectra, with the only change being what we selected as the first and last data points in the end. So that appears to work well. When you have very broad bands, and this particular one is the spectrum of liquid methanol sitting on top of silver nanoparticles, ATR spectrum. And in this particular case, the baseline depended on whether you started at low frequency or started at high frequency. So in this particular case, the obvious way to do it is to start in the middle and work your way out both ways. And now it works really well. There's a spike in this spectrum for some reason which I can't even remember, but this was in the Chamber of Horrors, and so that it worked pretty well, even when you have a fairly broad band like the 08 stretch of methanol. We tried this with synthetic spectra, in this case synthetic bipolar spectra, and again you can see that even though the baseline that we put on there was ugly, it handled it pretty well. A little bit of difference at the ends, but not too bad at all. Interestingly enough, what we then did was just put we wanted to see whether this was having any effect on shapes of the band. So we constructed a noise-free Lorentzian, and which is shown in the green dots here, and then put some noise on there and did the baseline correction. And this is the baseline corrected spectrum. And what happens is that it thinks the low gradient wings of the band are baseline. So the end result of that is that it sort of converts a Lorentzian into a Gaussian, and but it doesn't distort the band at all. I mean, it's still there at the right frequency, and the same thing for a bipolar band. So it's actually a slight resolution enhancement as opposed to a resolution degradation. So at this point, now I had to start thinking. I knew I had this talk coming up, and we started thinking about VCD, and was there a better way of handling bipolar spectra beyond what was published? So everything that I showed up till now was in that paper in the May issue of last year's Applied Spectroscopy. And what's in red here is what Andy did to improve this and make it a little more rigorous for bipolar spectra. I don't want to get into the details of this. A, there isn't time, but B, it's really kind of complicated. And we've just submitted a paper on this to Applied Spectroscopy. So hopefully the referees will like it. And if anybody wants to find the details of this when you've seen it, once it's accepted for publication, I'll be happy to send it out to you. There's a custom filter design in the third phase, and you can use two matrices. This one here, I cleaned it up on the other program. That R should not be there. This is the B is the baseline of the raw spectra, and the B sub R matrix is where the residuals have been taken into account. It turns out that they don't make very much difference which of these two matrices that you use. So anyway, basically what we did before was to pick the maximum and the minimum in each of the 64 regions of the spectrum. Now what we're doing is taking every point. In this particular case, there's just the two neighboring points showed, and showing how the derivative changes. But we actually do that with all the with all the data points. This is just two of them, and the median of these is turns out to be the baseline, and it works remarkably well. So does this work on these VCD spectra? Here is the spectrum as received. Here are the two baselines corrected with the two different matrices, and the result is very similar. I mean, basically, it doesn't really matter which one you use, and it gets over the carbonyl artifact on here, just basically the spike on this particular case, and but has a little difficulty at the very end of the spectrum. So how do you handle this part at the end of the spectrum? It'll handle a spike very nicely. It'll correct the spectrum in an automated fashion. And we looked at various methods of correcting for the solvent absorption at the end, and this is basically adding a sigmoid at the end of the correction. And there are some methods which actually get much closer to to where you have total absorption than others, and that's the one that we ultimately selected. One of the things which is quite difficult to do is to just baseline correct noise. And so here's a noise spectrum. It happens to be a VCD noise spectrum. And here are the two baselines that we calculate. And I'm not showing the end result because it was a mess. You can't really look at noise superimposed. But you can eyeball this and see that it actually seems to calculate a baseline, even when you have just pure noise. So finally, I realized we haven't used anything other than Camphor on looking at this. Now, really, I mean, that was clearly a mistake. So back on the email to Jordan Nafee and say, can you send us a spectrum with a bad baseline that isn't Camphor? And he said this particular compound here, whose name, according to my organic chemistry colleague, is shown down here. It's a chiral compound, and this is the VCD spectrum as sent to us. It's got a bad baseline. We used exactly the same parameters that we used before, and you get good baseline correction. So this seems to be a technique that works with unipolar bands, bands going in one direction, bipolar bands, noisy or not noisy, spikes or no spikes, and to a relatively limited extent, solvent bands, even, which are the most difficult things to compensate because they're not really baseline. This, I think, well, certainly it's the most versatile baseline correction technique that we've used in our lab, and it seems to work well on all sorts of spectra. So I'd like to leave you with that with that thought. I'd like to thank a couple of people. I'd like to thank Hu Sheng for starting all this, and we'll finish it, I guarantee you. I'd like to thank Jordan Nafee, who sent me the VCD spectra and has been very willing to interact electronically. But especially, I'd like to thank Larry and to congratulate him because I was really surprised that he hadn't won the SSP award beforehand. But it's an award which is richly deserved, and I really appreciate being part of the symposium. Thank you. That wasn't water vapor. I recognize water vapor. That.
You can't recognize water vapor in the VCD spectrum because water is not chiral, but because it absorbs the light, that's what we get.
Yeah, but the noise was exactly the same where water doesn't absorb. It was. So it was.
I get the Steve's question actually in that line, is if there is anything we can do, because that's one of our biggest problems, because we can't control how much vapor gets in the spectrometer. If there's anything.
Oh, it'll work now. Okay.
Yeah, if you look at the next spectrum.
There's not much difference in the noise here and the noise, and there's a little bit. Okay, some of it's water vapor, some of it's a reduction in energy because of water vapor. I think that's what you're saying.
Bruce has a question.
Yeah.
It looked, you addressed this issue of whether your algorithm changed band shape, and it did look like you were pretty good about preserving intensities. But have you looked at a case where you've got a spectrum with radically different intensities and bands widths? Does it make any difference if you've got really broad stuff someplace, really sharp stuff in another? And are you confident that you maintain intensity?
That was where we were looking when we were looking at the methanol spectrum, where you had that broad OH. That was the one that we've really looked at, and so providing that you don't start on that band, That you could start somewhere where the baseline is reasonably flat. It doesn't have to be as flat as it was on that spectrum, but if you start where the broadband has got some gradient, then it has problems there.
But how about the really sharp bands? Are those intensities maintained?
Yes, yes, they're well maintained. We haven't actually looked at the area. Something that we should do is actually look at the area. Is the area that's cut off on the wings compensated by the peak of the band? It's certainly higher, but it looked to me as if there was a little more area in the wings than there was above that, and it's something we have to do.
This is the VCD noise spectrum or the noise in the VCD spectrum? If you go to the next slide, just extra.
This one?
Yeah, if you look between 1600 and 1800.
Oh, that's certainly that's water vapor. Yeah,
Yeah, that's water vapor.
yeah. That I agree, absolutely, yeah. But in terms of the noise spectrum, that's pretty much random noise which gets bigger at the ends of the spectrum.
So my question is there anything, can you modify your algorithm somehow to recognize that very, very sharp bands that are, like resolved bands from the water vapor, somehow just ignore them, move them out, or
Take them out.
That's sort of like the old galactic zap function where you could take CO2 out and graft in noise into where CO2 was. And we're trying to baseline correct. We're not trying to spectrum correct. We're trying to baseline correct. So obviously when you're doing baseline correction, the sharper the band, the easier it is to baseline correct. That's always the case.
It's a nice technique for a lot of utilities in electron spectroscopy.
Yeah, I think so.
Well, thank you very much.
Thanks.
Well, this concludes our symposium. And before we disperse, I'd like to thank the speakers as well as all the participants in recognizing Professor Nafee on his accomplishments. Please join me in congratulating him again for this very distinctive honor. Have a nice evening and enjoy the rest of the stay at Pittsburgh Conference. Thank you.